deep feedforward neural networks. We started some of these things. I try to summarize what we talked about before into a slide here that has graph and equations. So the upper set of equations represents the multi-layer neural network, which is a nested neural network, which really captures what goes on in this black graph. So you have, view it as a vector or a matrix. We're viewing it here as a vector. A sample K comes in and moves from left to right, starting with SK, moves through this network, and the network is just a repetition of the same modular form, which is a linear mapping plus a bias. And then nonlinearity, represented here as a circle. Okay? So that's a single layer. 1. The soup here stands for the layer. And then the output of nonlinearity is A, which stands for activation. Okay? And then this output of the first layer, A1, hits the next layer, which is layer 2, represented by the parameters of matrix W soup 2 and B soup 2, to give you the X2. And I'm using X to stand for a state. And X also represents another coordinate system, to just keep the thinking there. And then you hit it with nonlinearity. I'm sorry I don't have a good pointer here. 2 and so on. And you decide how many layers. And deep neural networks says basically you need many of these cascaded layers in order for us to capture a complex mapping. Because we're going to view that problems classification, detection, prediction, all of them represent very complex mapping if the data is very real. Okay? And let's say in this case we have n stages, and here's the mathematical compact form for it, where you can label the first entry here, S sub k, as A sub 0, which is an output. The input is just you label it at A sub 0, and then you have this nested equation basically represents your model. That's the model that you're dealing with. For this model, you define a cost. Often we use the word loss function, which is going to be, by definition, a scalar quantity. And this scalar quantity is going to be a function of all the parameters, implicitly, not explicitly. So, for example, if you have an error, this error is achieved if it's supervised learning, at the final stage, you define an error measure of some sort. That's a choice. There are other methods of defining an index or a loss function. From this error, you define it, and this thing becomes, in fact, a function, implicit function of parameters. And then you go to the gradient descent by a lot of different means. There's a huge literature on how to use optimization gradient descent techniques, okay, and different people favor different methodologies of deriving it. In this neural network, they favor the so-called backpropagation technique in deriving it. It's a method of doing it. So from this cost function, if you crank out that gradient descent and you order things in a certain way, you can actually have a temporary parameters, implicit parameters or vectors called lambdas, intermediate variables, to simplify the representation of the gradient descent. And that intermediate variable actually could be laid out as a network, which is the red network here. And this network is going to be propagating backward in the sense that it's going to take as input the final error that you have at the output here, and that's when it's going to drive this network backward. So to obtain these lambda parameters, or these so-called e to the soup, which designates the layer, you have to drive it with this error signal, pass through all these blocks. The square red block, as I mentioned last time, it's actually derived from the circle here, which is the activation function, by taking the derivative at this state. So, and then you have another parameter, intermediate parameter lambda, and this parameter is going to be compatible with the transpose of the corresponding weight, because that's the same weight here, transpose, and you pass it. So there's a first forward pass, then backward pass, and the backward pass here is going to generate all these intermediate parameters called lambdas or deltas, depending on what you want the literature. Okay? And this is all basically simply taking the gradient descent of this loss function that you define. So what I have for you next is basically, and by the way, I noticed in the video that I use the word basically a lot. I'm just forewarning you. Okay? So, the backpropagating network, which is really extracted from the derivation of the gradient descent, and just having an architecture that models exactly the network that you have to have a nice graph, is represented mathematically with these equations. So here's the error at the final stage, and this error at the final stage is going to create a lambda, intermediate parameter, and this lambda is going to create an e, and you cycle through it, all the stages, to the first stage here, lambda. Okay? And then the next step is to have the change of weight for each one of these parameters that you have, for each one of those stages. Again, this is going to be laid out nicely, that every weight that you have here, or bias, is going to be obtained. Let's look at W2, for example, will be obtained by an outer product of, here, U2 is going to take lambda 2 vector, outer product of A1 transpose, which is an outer product which has to be A1 transpose. So here lambda I, the input to that stage, which is A to the I minus 1, and that updates this one. Remember, this S sub k, we can relabel it as A to the 0 to make it compatible with the equation. So we have compact equations. This is the change. This change, you can choose either to do it per sample, which is referred to as online learning, that every incoming data, you execute it, you get eventually this change, and then you can decide whether you're going to change the weight by this change of parameters, or wait a bit, doing the same changes over multiple samples, which is referred to as mini batch, and then you sum all those things, average them out, and then you have an average change. This change, okay, this change here is proportional to a scaled version of the gradient at that point. So when you do that change over multiple samples, which we refer to as mini batch, you're not really biased towards one sample or the other. You're taking a group. If you have any noise, you clear that noise up. You take the direction that is the average direction, which is typically the best gradient direction for this thing here. Okay? Any questions about the skeleton of the graph and the math? Yes?
I have a question about where we want to calculate lambda I. So
lambda I? I'm sorry?
Yeah, like, can you briefly say why we use like f prime? Like, what is the...
Yeah, it's, remember, we're deriving these equations. We're not showing you the derivation, it's just those derivations are byproduct of executing the gradient descent. And the gradient descent, by its nature, taking derivatives. Remember, we talked last time, taking derivatives and then chain rule. So when you pass through some nonlinearity, you take the derivative of that nonlinearity. So that's why everything is really an outcome of this gradient descent, because it's taken executing derivatives. Any other questions? Okay, so let's see what the set of equations are. My set of equations, I have equation of the network on top, and I'm relabeling whatever input as AI just to make the equations codable, easily codable. Okay? And then we have another set here, which is the back propagating. The processing is happening backward in stage, from the final stage to the first stage, or layers. The word layer and stage could be interchangeable. And then the weight of the change of weight. And as I said, typically we don't really make a change per sample and basically update the weight. No, sometimes we do it over many mini batches, several of those things, to make sure we have a good direction of the gradient to move up to the next sample point. Any questions about this other slide in terms of equations? So these are the equations, and they are given to us here in vector format. And I love this notation, by the way. Why is that? Because I'm using X to represent a state, which is a coordinate system. Remember, I think of the mapping as just moving from initial coordinate system, whatever, which is the physical coordinate system, where data could be actually smudged together and cannot really classify it nicely, into intermediate stages of coordinate systems, until eventually unravel the data, this transformation, if it's successful, and makes certain classes collectively together, whereby the final layer can do a simple classification, which is the data becomes nicely, we use the word linearly separable, which means can be partitioned by hyperplanes. Okay? What I have for you here, if you want to dig in on how to derive this thing here, the easy way of going about it, this is a scalar J and a matrix at layer I. So it's, if you want to compute, if you're really sophisticated in linear algebra, you could go ahead and just do things in vector matrix calculus. But an easier process, perhaps, for most, is to just look at it element-wise. So you look at one element in that matrix, okay? And I'm using this E or J is the same here. And you take a scalar, so a scalar over a scalar derivative. That's what defines the change of a component of that matrix. And I'm labeling the component here as Kj, some arbitrary component of a matrix, of some layer. And when you look here as scalar, then calculus, you can actually, the first thing you do is partition this one into two pieces by the chain rule. First, this weight is going to connect, has an output connected, which is, in my notation here, is an X, some X. So this WK is an element that connects an input J, component J, into an X, which is component K in this case. So you partition to two pieces. One is like this, which is the output connected to that particular weight of interest, whatever that weight may be in the network, right? And you leave the other one. By the chain rule, this E has to be with this XK, and then the XK with respect to this one. This XK, we chose it because it's connected to that particular weight. And when you execute this derivative, with respect to that weight, you're gonna get the output of the previous stage. I'm just using Yj. Unfortunately, here the notation is different. Yj is an output component, J, of the previous. And this one is also a scalar. This whole thing here, in parentheses, with the negative sign, this whole thing is a scalar derivative over xk, which is some state. We just say we're going to label that as this lambda. So this lambda component is going to be defined by this derivative. And then you can go home offline and do the calculus for this part here, and you're going to end up with the network. Okay? But right now, at this stage, you split the gradient into two pieces. One is easily obtainable, which is this part. This part, with respect to the parameter, is going to give you the input that's driving that parameter. The input of that parameter is the output of our previous stage. And so is this guy. This other one, which is complex, you just label it by a new parameter, lambda k, and then you can go home and derive that lambda, okay? Or you can have somebody else do it for you. So this is just giving you a way of how this network, the other red network, the shadow network, the sensitivity network, the backpropagating network, all these terminology are the same, how it's derived, okay? So this is the basically backpropagating, which is a two-phase process. Feed forward, you have a sample, you pass it through, you compute on some form of an error, then you pass it back in two stages, then you do the update of that particular pass. And often you do it for multiple samples, which we call it mini batch, to strengthen the direction that you're going to choose. It's going to be an average direction, before you actually apply it to your particular weight. Okay? And then you apply it to the particular weight, then you have the next group and so on. So, question. This stuff is known for many, many years. This stuff is known for many, many years from the 90s, okay, and earlier, okay? In different forms. The only thing is that people like to derive it maybe more elegant way than another way, but it's all the same stuff. So what do we mean by deep neural network? So obviously the depth thing is that you have this number of stages or layers has to be many. The catch is when you have many, then you have a problem using the gradient descent in achieving performance or learning. Doesn't work very well, okay? In the old days also computers were slow, so you have many of those things. The update, just if you're unlucky and you start with some random choice that's pretty bad, you could be stuck in a local minimum. And it doesn't really achieve the classification goal that you have, okay? So here's a list. What makes a deep neural network, what makes deep neural networks function is that one, obviously, the deep layering. In the old days when we had deep layering, if you have more than 3 with computational stuff, you really can't achieve much. That's one. So now the first thing is you need depth. Also, the choice of nonlinearities is important. Historically, we selected the so-called sigmoid or logistic function, and this is a definition for it. You can look up the definition basically. It's a sigmoidal function. It's between 0 and 1, and it's a shape that's a sigmoidal standard. There's an extension of that called a softmax. I urge you to look it up. You can always look it up in the book. It's well defined, and I don't need to write it here. The hyperbolic tangent, which is obviously a form of sigmoidal function, which is between +1 and -1. It's hyperbolic tangent, and has a specific definition, has a nice properties. These are the things here that have been used in the past. People more recently use something called rectified linear, which is really, if you have an input to that nonlinearity, is going to be 0 unless that input is positive. Then it becomes equal to that input. So really it's equal to 0 and then basically a linear slope of 1. So it so happens in the recent years, around maybe 2006, people have used multi-layer neural network, and when they injected this rectified linear to this model instead of the other models, it actually was able to pull itself from local minima and was able to have demonstration of performance, okay? So I would say that's one wrinkle that says, okay, that overcome the problem that the gradient descent did not work for deep networks. So everybody knew that we need a deep network to solve a complex problem, But this gradient descent did not work for multi reasons. I mentioned like the computational speed was slow, resources were maybe not there, but also the functions were not helping or were basically forcing the network to be stuck in local minima. Unless you spend some time and get lucky, you could initialize things the right way. So with this rectified linear, success rate is much higher than before. And that people notice it something in 2005 or something like that. The other thing, when you have multi-layer network, we didn't really talk about connectivity. We assume in general that every input is connected to every basically output. So you have a full matrix. It turns out you have more parameters that way, and therefore you're likely to get stuck somewhere because you have a high dimensional parameter space. And there's a lot of theories about for this number of parameters, if you have this number of parameters, how many data sets for training do you need and how much time and all these things, and theoretical work that we're just mentioning right now. But the point is you can lessen those parameters by reducing the parameters by having local connectivity. So instead of having full matrix, you just have basically a local connectivity matrix. So every output here doesn't really connect to every input, but connects to a portion of those inputs, okay? And also that leads to another concept called sparsity. So when you have multi-layers, if you have them all connectivity, you're perhaps overdoing it, overfitting. So you need basically local connectivity, and also you can achieve local connectivity by sparsity, meaning that you're going to have every intermediate state representation will have a lot of zeros in the representation. And you can achieve this a lot of zeros also randomly by what's referred to as dropout technique, which adds stochastic nature to the update law. So instead of having the gradient descent being deterministic or near deterministic, you want to have more stochastic nature to it. And one of these techniques that has been very successful is actually to have a percentage, random percentage of every hidden layer outputs or inputs set to 0. You drop them out, which means that you're really randomly injecting some noise in the update process. And it turns out that that technique prevents the gradient descent technique from getting stuck in local minima. So if it gets to those local minima, with this stochastic nature, it actually does not prevent from update. The other thing is also, instead of just the raw gradient descent as we described it here, there are a lot of variations of gradient descent. Often they play with the so-called eta, which is the learning rate. We have another parameter, which is, I call it here alpha, which is referred to as the momentum. So these parameters, which are labeled as hyperparameters to distinguish them from the W and B's, which are the parameters of the network, there are a lot of different techniques of either selecting those things or rederiving a variant of the gradient descent that increases the performance in the numerical technique and updates. The other thing that was very powerful also, the availability of a huge data set, the ImageNet and other data set that has been groomed and well separated and tested to enable researchers all over the world to benchmark their approach and test the performance of these things, the availability of research sources and the environments that are created and the libraries that we have basically help out in improving these techniques. Success stories that came out, I guess, as recent as 2006 and 2007 demonstrated performance in key applications in speech recognition, image recognition and detection. And now we have, every year we have an ImageNet, which is a competition in image detection on huge data set that sets the bar for performance. Any questions about the framework and the network as we have it so far? Okay.